Hi students, today I want to continue the preparation methods, two more preparation methods we have. Actually, they are not much important, but better to know about this. That is Hansadeker-Borodine reaction. Hansadeker-Borodine synthesis or Hansadeker-Borodine reaction. Here, Hansadeker-Borodine reaction is mainly used for alkyl chlorides and alkyl bromides preparation. Here, how we can give this is RCOOAZ. This is called as a silver carboxylate. The silver carboxylate reacts with either Cl2 or with Br2 in the presence of a solvent carbon tetrachloride, and this is forming RCl plus here Az and one chlorine atom released as AgCl plus the remaining compound is CO2. So carbon dioxide is released. If bromine is taken, we are getting RBr plus AgBr plus CO2. Okay, so here silver carboxylate reacts with either chlorine or bromine in the presence of a solvent carbon tetrachloride to form alkyl chlorides or alkyl bromides. And in this, the yield, order of yield. So here order of yield. If you are taking alkyl halide which is primary is more than secondary is more than tertiary. So a primary alkyl halide is formed more easily and better yield than secondary and tertiary. Why? Because is tertiary alkyl halides undergoes to elimination reactions mainly, and this is actually a free radical reaction. This occurs through a free radical mechanism. Here, free radical reaction means what is the mechanism? The simple mechanism we have here first RCOOAZ reacts with suppose bromine is taken Br2, then it is forming RCOOBr plus AzBr. And next step, RCOOBr reacts with, not reacts here, it is decomposing. In the presence of sunlight, decomposes to give RCOO free radical plus Br free radical. And this RCOO free radical again decomposes to give R free radical plus CO2. The CO2 molecule formation occurs, and in the next step R free radical reacts with RCOOBr and it is giving RBr plus again RCOO free radical is formed. This is free radical, RCOO free radical. In this way, alkyl bromide, or if chlorine is taken, we will get alkyl chloride. So this is the mechanism occurring in the Hansadeker-Borodine reaction. Okay. In this process, this is the slow step or it is a rate determining step. Here this is actually called a chain initiation reaction and this is called a chain propagation reaction. Next one, Birnbaum-Simonini reaction. Birnbaum-Simonini reaction. Here in the Birnbaum-Simonini reaction, if you are taking, it is actually also Hansadeker-Borodine reaction. Suppose if we are taking same silver carboxylate, and for example in this process, if you are using iodine, if you are using iodine, then what happens means it is forming RCOOR. Here two molecules of RCOOAZ is taken, then we will get RCOOR plus AZI and CO2. What is the product actually? Yes, the product is an ester. It is not forming what? Alkyl halide is not formed. That is a very important thing to remember. Here it gives ester only. It doesn't give alkyl halide. So better to remember, if a silver carboxylate is given, if a chlorine or bromine is given, okay, you write this product. If they are giving iodine, generally this is two molecules and this is one molecule. In 2:1 ratio they react and forms an ester instead of forming alkyl halide. This reaction is called as Birnbaum-Simonini reaction. Okay. Next, physical properties. Physical properties of alkyl halides. Here in the physical properties of alkyl halides, first one, if you are taking methyl halides or chlorofluoromethanes are, and if you are taking ethyl chloride also, C2H5Cl, they are gases. So methyl halides means methyl fluoride, mainly methyl chloride, methyl bromide, and chlorofluoromethanes and ethyl chloride are gases, and if higher alkyl halides are taken, they are present in liquid state or they are present in solid state. Okay, so the lower alkyl halides are only gases, the higher alkyl halides are liquids or solids. Okay, next, second point. Here, if this compound's solubility is taken, generally alkyl halides, it is looking like a polar compound, Rx minus and R plus is present, so it is looking like a polar compound. But here they are less polar and they are not soluble or almost insoluble. Insoluble in water. Why they are almost insoluble or less soluble in water? Because suppose if it is taken Rx, here it is a H2O molecule. Generally between H2O molecules, what is present? Yes, there is a hydrogen bond. Between these two, there is a hydrogen bond. If that hydrogen bond is broken and if there is a bond formation between these two, means if this is formed or newly it is formed, then it is called as soluble, not insoluble, soluble. Okay, but the energy required to break this H2O hydrogen bonds is much more than the energy released due to the formation of a bond between water molecules and alkyl halide. So, never water molecules hydrogen bonds are not broken easily, and so the water molecule and alkyl halide when mixed, the alkyl halides are partially or very less soluble. Why the remaining amount is soluble means a little bit energy which is more, means we can say hydration energy. Okay, that is more when compared with the bonds between hydrogen H2O molecule energy, and so they are a little bit soluble, or some compounds are soluble. For example, if they give, means they are having more energy between these two bonds, means water molecule and alkyl halide bond is giving more energy than the water molecule bond. So, okay. Next point. Third point, densities. Here, alkyl fluorides have less density than alkyl chlorides. Alkyl fluorides and chlorides are having less density than water, and it has more density, that is alkyl bromides and alkyl iodides. So fluorides and chlorides are having less density than bromides and iodides, it is clear, and water is having more density than alkyl fluorides and alkyl chlorides. That is important thing to remember. Water has more density than fluorides and chlorides, and bromides and iodides are having less density than water. Next, fourth point, when alkyl halides are taken on copper wire and on burning, copper wire and on burning, they burn with a green edge flame. Green edge flame. It is also a detection test or identification test of halogens. This is also called as a Bilstein test. Bilstein test for alkyl halides detection or identification. Which alkyl halide is present we can't get, but it must be halogen. It must be containing a halogen. So the halogen detection or identification test. Okay, and here if we are taking alkyl iodides, mainly particularly alkyl iodides, these alkyl iodides on decomposition, it converts into violet color. Violet color, iodine gives a violet color. Okay, so alkyl halides gives green edge flame on burning with copper wire, and alkyl iodide on decomposition means in light on decomposition gives a violet color. Okay, next point. Next point, melting points and boiling points. Here melting points and boiling points when we are taking. In this melting points and boiling points generally that depends on two factors mainly. One is molecular weight, and next is branching. The next one is branching. Here if melting and boiling points are taken, whenever molecular weight increases, the melting points and boiling points simply increases. Here we can take boiling points also. Molecular weight increases, boiling points and melting points increases. And next, a number of carbon atoms increases. When number of carbon atoms increases means parent chain carbon length is more, carbon atoms increases, then melting points and boiling points increases. That is also one point. Number of carbons increases. Next, suppose if branching is increasing, branching increases, and branching increases, what happens? The melting points and the boiling points generally decreases. For example, if you are taking CH3, CH2, 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 Cl, this is a N-butyl chloride. And the second one, CH3, CH, CH3, CH2Cl, isobutyl chloride. And next one is CH3, CH3, CH3Cl. This is called as tertiary butyl chloride. N-butyl, isobutyl, tertiary butyl chloride. Whenever N-butyl chloride is taken, it is a straight chain molecule. Isobutyl chloride has a little branch. Tertiary butyl chloride is having more branching. And so, whenever the number of branches increases, the melting points, boiling points decreases. Okay. Next example. If you are taking ortho-dichlorobenzene and if you are taking meta-dichlorobenzene and if you are taking para-dichlorobenzene. First of all, we will check the melting point values. That is important one. Here the melting point value of this compound is 256 Kelvin. The melting point is 256 Kelvin and this is 249 Kelvin. The melting point value is 249 Kelvin and here the melting point value is 323 Kelvin. Please remember it is a specific, it is looking abnormal. Okay, so it is having 323 Kelvin. It is a 256, it is 249 and this is 323 Kelvin. Why they have this type of melting points? Can you guess? Here 256 okay ortho dichloro and this is having meta, ortho to meta decreased. Meta to para also decreases na generally. If you compare ortho to meta decreases, meta to para also decreases. But why this is having an abnormal melting point, high melting point value? The reason is due to symmetrical, due to symmetrical structure, symmetrical close packing structure. Due to symmetrical close packing structure. Here, because of this symmetrical means it is a symmetrical law. The molecules can arrange closely. So, because of the close packing symmetrical arrangement of this para-dichlorobenzene, they are having higher melting point values. Okay, so please remember first melting point values. In the melting points only we have very abnormal values. In the boiling points, here if you are taking the boiling point values, here it is having 456 Kelvin and the next one is 443 Kelvin and the next one is 448 Kelvin. A slight higher value is only observed. I think it is also 446, not 43. It is 446 Kelvin. Okay, 456, 446, and this is a 448. A slight increase is only observed, but here for this, it is a very high increase. Okay, so this is melting points and boiling points of these elements. The next important point, CX bond length order. Suppose if you are having CH3F and if you are having CH3Cl and if you are having CH3Br and if you are having CH3I, which has more bond length? Definitely whenever the size of halogen atom increases, the bond length values increases. Next, second point, CX bond energy values. As we already studied, bond length is inversely proportional to bond energy, CX bond energy order. Okay, and the CX bond energy order is taken, which will be higher, CH3F greater than CH3Cl greater than CH3Br greater than CH3I. But very important thing is dipole moment order. dipole moment order. Here this is important. Previously they asked the question also, dipole moment order. Dipole moment order of these molecules if you are taking. The highest dipole moment is observed for CH3Cl, and the next one is observed for CH3F, and the next one is observed for CH3Br, and the next and least is observed for CH3I. Why? CH3Cl, chloromethane has higher dipole moment. As we know, dipole moment mu is equal to, I am giving the formula, it is delta into D or delta into L. Delta means what? Charge on any one of the pole. D means bond length. Here any one of the pole means, I am writing just simply, it is a chlorine, partial negative charge. This is partial positive because chlorine is more electronegative than carbon. So the charge on any one of the pole and the distance, d means distance between two atoms or bond length simply. Whenever the dipole moment values are taken, why we are having this type of order? Why CH3F is not having more? Fluorine is having a high electronegativity, so it has high charge now. So compared with chlorine, fluorine has a high charge now. But bond length values also you need to consider in calculating the dipole moment due to more CCl bond length. Due to more CCl bond length, the dipole moment of methyl chloride is more than methyl fluoride. That is the reason for high dipole moment of chloromethane than fluoromethane. Okay. And it is better to go through the dipole moment of CH3Cl, CH2, Cl2, CHCl3 and CCl4, which has more dipole moment. I think you can guess easily, very easily about this one. Mu is equal to 0. And here CH3Cl has highest dipole moment than Cl2, than Cl3 and CCl4. And another example and another order, CHF3, CHCl3, CHBr3 and CHI3, which has higher dipole moment. Yes, you guessed correctly. CHF3 greater than CHCl3 greater than Br3 greater than CHI3. So this is a dipole moment order. And I think you know this also. This is chlorine, chlorine, and here this is chlorine and this is meta position, and this is para position, para dichlorobenzene. Which has the highest dipole moment? Tell me, which has the highest dipole moment in this? Here, dipole moment, I think you know about the dipole moment representation. The arrow pointing towards more electronegative atom we can write. This is the arrow pointing towards chlorine atom. Here also the arrow pointing towards chlorine atom, and this is the arrow pointing towards chlorine atom. Here this is this direction and this is in this direction. Now tell me what is the dipole moment for para-dichlorobenzene? Yes, this is equal to 0 because both are in opposite direction. You know dipole moment is a vector quantity. It has both magnitude and direction. In opposite direction it will be cancelled. And here how much is the dipole moment? And here in this ortho and para, this is called as ortho-dichloro, and this is called as meta. It is called as meta-dichloro. In this two, which is having more? Para already having 0. In this ortho-dichloro and meta-dichlorobenzene, and meta-dichlorobenzene, which is having more? Tell me. Here orthodichlorobenzene, metadichlorobenzene, when you compare, it depends. Dipole moment value depends on theta, that is called as bond angle. Okay, here what is the bond angle? Can you guess the bond angle? I am writing just here. Here this is the angle. This angle is equal to 60 degrees. And here the angle is, the angle here is 120 degrees. So bond angle is lesser. So ortho has more than, meta has more than para. Okay. And I'm giving a question for you. Tell me the order of dipole moment for these molecules. I'm giving the question. Here this is a chlorine and this is a methyl group. And second, this is A. I am writing as A. And this is B. Here this is a chlorine and this is methyl group. And C. This is chlorine and this is methyl group. Tell me the order of dipole moment. You just write in the comments box. So tell me, write the order of dipole moment for these A, B, C molecules. Okay.